Hello, in this video we're going to look at how to differentiate the functions e to the x and ln x. So here is a graph of y equals 2 to the x, that's the line in green, and its gradient is the line in purple. And you can see that they're the same shape, they're both exponential functions, but they're not identical to each other, and the value of the gradient is always less than the value of the function. Here we have the graph of y equals 3 to the x in red, and also the gradient in purple. And these are a bit closer to each other, but you can still see they're not identical, but this time the value of the gradient is always slightly more than the value of the function. So we saw that the gradient functions of 2 to the x and 3 to the x were both the same shape, but the gradient of 2 to the x was always less than 2 to the x, and the gradient of 3 to the x was always more than 3 to the x. So that implies that there's probably a value of between 2 and 3 for which the gradient of a to the x will be the same as itself. And that is indeed the case. There's a number which is about 2.718281828. It looks like it's going to recur, but it doesn't. It's an irrational number, and we call it e. And for that value, e to the x always has the same gradient as the value at that point. So the rate of change of the curve is the same as the value of y at each point. So what that means is that there is a function which we call e to the x, where, as I said, e is just a number, about 2.718, for which, when we differentiate that function e to the x, we get the same result, e to the x. Okay, it's the only function in existence that does that. Also, if we have e to the kx, then when we differentiate that, we get k times e to the kx. So it's still got the same structure, it's still e to the kx, but it's been multiplied by k. So that's e to the x. We're now going to look at how to differentiate log x, ln x, and bear in mind that e to the x and ln x are inverse functions of each other. So we're basically saying if y equals ln x, then what is dy by dx? So this is how we go about it. So we start off by saying that y equals ln x, but the first thing we do is to exponentiate both sides. So we get e to the y is equal to e to the ln x, which means that x equals e to the y. If we then differentiate both sides with respect to y, so dx by dy, as we've already seen, if we differentiate e to the x with respect to x, we get e to the x. Similarly, if we differentiate e to the y with respect to y, we're going to get e to the y. For the next step, we reciprocate. So rather than having dx by dy, we have dy by dx. But of course, if we reciprocate the left, we have to reciprocate the right, which gives us 1 over e to the y. But we already know that e to the y is the same as x. So therefore, dy by dx equals 1 over x. And that means that we've got an expression for dy by dx in terms of x, based on the fact that we started with y equals ln x, dy by dx is equal to 1 over x. So now we're going to look at how we might differentiate a to the x, where a is any number. So we write y equals a to the x, and then we use the fact that e and log are inverse functions to write a to the x as e to the ln a to the x. We can then use the rule of logs that turns indices into coefficients to rewrite that as e to the x log a. And then we can use the rule that we just met, which says that if we have e to the kx, that becomes k e to the kx. So in this instance, we've got k as ln a. So when we differentiate it, we get ln a times e to the x ln a. Of course, e to the x ln a is the same as y. So dy by dx is log a times y. And again, y is equal to a to the x. So that means that if y equals a to the x, then dy by dx equals a to the x log a. So if y equals 2 to the x, then the differential will be 2 to the x log 2, and so on. And if we had e to the x, then we would get e to the x log e, and log e by definition is equal to 1. And we can do exactly the same with a to the kx. So we can write that as e to the log of a to the kx, bring the kx down as a coefficient, and that gives us e to the kx log a. So now we've got k log a as our constant that we're timesing x by. So when we do dy by dx, we get k log a times e to the kx log a, which can be replaced with y, and in turn that can be replaced with a to the kx. So if y equals a to the kx, then dy by dx equals a to the kx k log a. So in summary, If f of x equals e to the x, then so does f dash x. And if f of x equals e to the kx, then f dash x equals ke to the kx. If f of x equals ln x, then f dash x equals 1 over x. And so it also does if f of x equals ln kx, because ln kx can be written as ln k plus ln x. And when we differentiate a constant like ln k, we get 0 anyway, so we get the same result. And then finally, if f of x equals a to the kx, then f dash x equals a to the kx k ln a.